Okay, so today we don't have any internet, which will teach me to rely on the internet too much. For the students that are not physically here, I guess all I can do is record the class, and then we have to post it on YouTube afterwards, so they won't be able to join the class at the moment. NTNU Wi-Fi I can use, but not with that computer because it doesn't have the Wi-Fi access card. I can use it on the laptop, but I don't think I can project. Set that up. Okay. So, but even here, I don't have good internet. It's very slow. Let's see. while this is running, okay, we can start with the homework. Can you turn on the recording? Yes, it's already running. And Discord. Oh, Discord is still downloading. Okay, so last time I said we're going to start doing introduction to Python today. I actually wanted to do mine in TypeScript, just to do it a little bit differently. We can do that next time. So the problem that I asked you to solve was homework. I cannot really check Discord, but what did I ask you to solve? The monotonically increasing attack, right? Strictly monotonically increasing. So we were supposed to write a function which takes in the list and you have to check if the numbers keep going up, basically, right? Strictly monotonic means that this is not allowed, line 9, so it cannot be the same number, right? If it's just monotonic, this will be okay, and this will be definitely wrong. In this case, the function is not monotonically increasing. Network change. Okay. Line network change. Oh, and oh, that's why it's running. Okay, but then we can connect the Discord on there. That internet is faster. Okay, never mind. It's too complicated now. We'll just record it and post it afterwards. But I don't think any of the internet is fast enough to do that. So let's have a look and see what you did. Okay, then we do another one. You Visual Studio. Okay. Cannot sign in. Okay. Okay. But do you have any Python installed at all? on these computers. Okay. Yeah. Uh, so here we have some code that actually works, but it's not very efficient. So let's see if I can get you guys started up. Word, no, nothing Word will not work. Code, no. Only thing you can try is Notepad. Okay, and yes, here I also cannot connect to Windows. God, now I will be connected. Okay, so let's have a look at the code then. I will just here. So I want to define a function that takes as input a list, right? And then I want, and what you implemented was basically this. Okay. I didn't install the Python environment. Python 3. So here it runs. That's the code that I wrote. What does this actually do? It creates a list, yes. So here we're using something that's Python specific. The rest of the code, this part here, the top part, would look the same even if I used a different kind. It would look the same in pretty much any imperative programming language. So whether I write this particular code in C or C++ or Python or JavaScript or TypeScript or Rust, um, that part, if I use the imperative programming paradigm, it would look very much the same. So for Python, we have to remember it's an imperative programming language. Which means what? Okay. So now we're in this core 2 unit. So what does it mean for an imperative programming language? For a programming language to be called an imperative programming language means that we use a lot. That's true. Most of the programming languages that you are familiar with are all imperative programming languages. So it's by far the most common paradigm for designing a programming language. So it is basically the thing that Java, C, C++, Python, Rust, Ruby, assembly language have all in common, sort of, because they're all based on the same paradigm. Not all programming languages are based on imperative programming language, but most of them are. The basic point is that in imperative programming, imperative means instruction, from the Latin, and it basically means that we focus on the stream of instructions that we send to the computer. Okay? So basically, we think about programming as giving one instruction or a flow of instructions to the computer to execute at all times. So we're mainly concerned with the flow of these instructions. now, now at modern times, more modern programming languages have combined the imperative programming paradigm with object-oriented programming. This is very common nowadays, OOP, object-oriented programming. So, what's the focus of object-oriented programming? What's the difference between C and C++? No difference. Object-oriented programming all focuses, not surprisingly, on objects. So, in that context, what do we mean by an object? No, this will be more imperative programming. Imperative programming is all about control. In programming language context, what we mean by an object is the combination of control flow and data structures. So in this case, our programming, our mental model of the problem that we're trying to solve is created differently. We sort of think about things in our program in an abstract sense, that where we can combine the control flow and the methods, the functions that we use, together with the data. So that's why that's what usually is called a class then, right? Because in a class, you combine your instance variables, right? If you want to represent a car, then you can combine certain instance variables. You can max speed, um, max weight, um, liters per kilometer, like so this is certain data, right? This is all certain numbers. You can have a position where you currently at, so this may be two numbers, x and y coordinates. And then we associate with this data, we associate certain functions, things that we can do, we associate control flow with them, so then you have instance methods like drive from to, or fill up. Here you can have logistic domain. I have a truck has to go all over Taiwan, deliver all of these packages, right? Then, what will be of interest would be how fast I can go, how much gas I have in the tank, what the maximum number of packages are that I can carry, how much gas I use while I'm driving, and where I'm currently at, for example. And then I can drive the truck, I can fill up the truck, I can load packages or unload packages, right? So this is what object-oriented programming focuses on, the use of objects. But imperative programming, we're looking at the control flow. And to understand imperative programming, you really only need to understand 4 or 5 concepts. You just need to know how to do 4 or 5 things. And then you can learn any kind of imperative programming language very quickly. So even if you've never seen any TypeScript code, then you can probably read it just fine and write it too after an afternoon looking at it. So what are these 5 concepts of control flow? The first one is sequence. And this one is very easy. It's all the programming languages, most likely all the programming languages that you are familiar with follow the same model as Python. And sequence just means in which order are the statements executed. So if you look at this Python code here, then the order is pretty. Somebody tell me I'm using the wrong mouse. The order here is pretty clear. If I execute line 17, then which line will I execute next? 18, and then 19, right? So the sequence in Python is the same as C, Java, any other, most other imperative programming languages. We execute things one line at a time. That's not necessarily the only option though, right? There are programming languages, for example, Occam. Occam is a programming language that was popular in the mid-90s for a transducer process, CPU, that was actually very interesting. It was a CPU that was built for massively parallel computer systems. So it had the connection hardware and the switches on board so that you could do parallel processes very easily. So in that kind of programming language, the whole idea was that we cannot build a single CPU that is running faster and faster. And you sort of see that happening, right? CPU clock cycles have not really increased much in recent years. So if you want to get more work done by and we have now the ability to build much larger chips. The yield on silicon wafer construction is going up. So we can now build chips with billions of transistors. I'm not sure what I don't have the internet right now to check. But about, last time I checked was probably about 7 years the largest computer components that you have in your computer, your standard desktop PC nowadays, would be what? What has the most number of transistors? If we use transistor count as a measure of complexity, then the biggest, the largest part in your everyday computer system nowadays would be, most people would think the CPU, like your Intel i7 or your Mac M1 or M1 Pro or M2 or your ARM core, right? But and they are certainly complex. But usually nowadays, the component with the most number of transistors is your GPU, your NVIDIA graphics card. Usually has about 2 times as many transistors as your CPU. The number of transistors, at the time that I checked, whatever the Intel CPU at that time was about 7 billion transistors. And the GPU about 15 billion. So now I think that complexity has gone up. I think now Intel i7 CPU has, if I have to guess, I would guess it's about 13 billion, whereas the GPU is probably topping 20 to 30 billion transistors now. Now the reason why GPUs can be built with or have more transistors is because the processing that you need to do for a GPU is highly parallel. Because you need to work on basically every pixel. Right? So the more you have, you can work on one pixel at a time, right? Then you only need a very narrow processing pipeline. But if you have more transistors, you can work, because the pixels are mostly independent, you can work on thousands of pixels at the same time. Then you need to use more transistors, but you can all execute them in parallel. So Occam was a programming language to use this idea of parallelism in order to speed up. And there, if you wrote a program, s is equal to y plus 5, so x is equal to y plus 5, s is equal to hello plus world, then these two statements will be executed in parallel, not one after another. Right? Lisp programming language, if you have a cont, which is basically like a switch statement, every time you evaluate a switch statement, which is called cont in Lisp programming language, the conditions are executed in parallel. Or they're not executed in parallel, they can be executed in random sequence. So it's not clear which one will be evaluated first, second, third, fourth. Right? That makes things very, very different. Also, if you program in VHDL or Verilog, then everything happens in parallel because you're executing in the clock cycle. So if you write this in Verilog, these are all executed at the same time. Nowadays, on a modern CPU, these kind of statements are also, because we're a superscalar with the i7 and the modern CPU, these ones will most likely also be executed in parallel, assuming that your pipeline is deep enough. But in Python, it's always one line at a time. In C, it's one statement at a time. It's always like that. And that's guaranteed by the language. So, for efficiency, it it's more efficient. You can write faster programs if you're allowed to reorder and execute things in parallel. But that makes it hard to reason for most programmers. It's more difficult to program in a programming language like this because this statement here, this is of course not a problem. These two are totally independent, these two instructions, these two commands. So I can execute them in parallel. However, this would cause a problem, right? Because if I execute x is equal to y plus 5 and z is equal to x plus 3, then I cannot really execute those two in an arbitrary sequence, right? Because I have to execute this line first, then this line. So your Intel CPU actually has shadow registers and pipeline, and it analyzes the data dependency, and then it makes sure that whether it can execute those two instructions in parallel or not. And it has some extra hardware to overcome some of the problems. So if it's a simple thing like this, where x is calculated here and needed there, it can actually use the shadow registers to pass the data along the computation. So it would even be able to execute those two in semi-parallel process, right? It's semi-concurrent, so more efficient. This one here is not so dramatic. Other fun things that can happen though is if you have more complex instructions. Now, functional programming is another programming paradigm. So there are certain programming languages that particularly focus on functional programming, and those would be Haskell, ML, FP, Haskell, what's the other one that's popular nowadays? They are not nearly as popular as Java or C++. Okay. So for functional programming, you have a different paradigm. The paradigm here is that you basically prefer pure functions. Which means that you don't have any state in your function. So what does that mean? If your function has no state, then that basically means no global variables or instance variables. So in this case, we think about functions just like mathematical functions, where if I call the function plus 3, 4, right? If I call function plus with arguments 3 and 4, then the answer is going to be 7. Hopefully, if your adder works correctly. And if you do not have any state, then there's a couple couple of cool things that you can do. If you can guarantee that the function is pure, then there is a couple of neat things you can do. One of them is you can actually cache your results, right? Because basically what it means is that if I call function 1 with argument 1, argument 2, argument 3, then it doesn't matter if I call it today, tomorrow, next Saturday, or 100 years from now, the answer is always going to be the same. Right? 3 plus 4 is always going to be 7. It doesn't matter when I call it. That's because the function does not have any state associated with it. So then you have huge advantage because one, you can run it, you can do caching. Right? If you have this function for a strictly monotonic, and I call it with some list, if I remember that result, I never ever have to call that function again. I can just remember, I can just cache the result and say, oh, the answer there will be true, or the answer there will be false. So that makes it much more, that may make my computation much more efficient. And the other thing is, if it's a pure function, then when I ask you to tell me what is 3 plus 4, or I ask you, also doesn't matter, right? So that means it's very easy to parallelize that kind of computation. I can just give it to any CPU. The answer that I get should be the correct answer. However, unfortunately, for most of the things, or a lot of the things that we need to calculate, actually, we do need state. For example, if I ask you, I have a meeting today at 1 o'clock, and if I ask you, how much time do I have until the meeting, then now, if I ask you now, you would say about 3 hours, 2 hours, 56 minutes. But if I ask you in an hour, then the answer would not be 2 hours and 56 minutes. The answer would be 1 hour and 56 minutes. Right? So now that means that function is not pure. There's some state associated with it, in particular the current time. So then you can say, okay, that I can fix easily because I can write a function. I would have to change my programming, and instead of implementing a function that says, how much time do I have to the current meeting, I would need to change it and say, right now it's 10:05, meeting at 1 o'clock, how much time is the difference, right? Then that function will be pure. So sometimes you can make the state explicit. You can make it one of the arguments saying the current time is important. So you put it into the argument list. That works. But often the state is not so easy to make explicit. In particular, with a lot of functional programming languages, and when you're not used to them, what happens quite often is that you have a statement like this. You want to write a program that converts temperature from degrees to centigrade. Degrees centigrade to Fahrenheit. In the US, they use Fahrenheit for temperature instead of degrees, right? Or in Taiwan. Usually the years in Taiwan are labeled, what year is today? 2022 would be the Western year, right? But when I get a contract from NTNU or an official document, it tells me that the year today is 111. Because the Taiwanese years start at the year of the Chinese Revolution, which will be 1911, right? So you can think about, you want to write an easy program because for me that's confusing. So I want to be able to enter the Taiwanese year, and then you enter 111, and then you want to generate output saying 2022, right? So you want to write this program, it's very simple. Um, but if you write this in a functional programming language and you write it like in this format, then very often what will happen is we think that those are mathematically pure functions, which means I can execute them in any order. So at the beginning, it was very common that you would do things like or enter the year, slightly different. You have like a print to enter the year, and then you want to read the current year from standard input from the keyboard. But if you run this in a functional programming, with a functional programming language, if you're not careful, what will happen is that it'll execute this year, this line, execute, read from the keyboard, but it hasn't printed the prompt yet. So nothing happens. You think your computer is crashed because it's waiting for input, but if you type 111, then it'll say, please enter the Taiwanese year afterwards, because the two lines are executed in the different order. So here our state would be dealing with the external environment of the computer. The keyboard, input from the user, databases, hard disks, buttons, mouse movement, all of that actually has state. So it's difficult to deal with that in a functional programming paradigm. But in Python, so that's just to show that the imperative programming language paradigm is not the only one. There's many other types of programming languages available, and in fact, Python includes some of the functional programming paradigms. Some of the things that you do in Python that you can actually do are borrowed from functional programming. So most modern programming languages have one main approach. Python definitely imperative programming language, but it also includes some object-oriented programming and some functional programming paradigms. Because it turns out that some of them are very useful even writing imperative programs. So now we know how to send different instructions to the CPU, basically, through to the interpreter. Then the interpreter will convert it into binary code, and then that'll be executed by the CPU. So we know a sequence. The next thing we need to know is your CPU nowadays can execute about 4 billion instructions per second if it's fully saturated, if you're running at full speed. So if you have to write 4 billion lines just to keep the CPU running for 1 second, then it will take you thousands of years to write any kind of program. So then you need to know about the technical term is called iteration, which simply means how do I do loops? What kind of loops do I have? And what kind of loops are you familiar with? For loop. And what's a for loop? What do you use it for? Like in this case here, for I in range, so that is a for loop, right? And actually this is not a for loop. In Python it's slightly different. Your typical for loop would be a counted loop. So from C for I is equal to 0, I less than 16, I plus plus. That's your typical for loop. It's usually used to generate iteration a fixed number of times, counted number of times. So 16, or this could be a variable here too. So you can say like C dot length or something like that. Right? But at the beginning of the loop, this number here is fixed. Even though you may compute it, it may be a variable. So this is a counted loop. What other loops do you have? While, yeah. And what do we use while for? Yeah. So here we have a variable number of iterations. So here I'm not sure how often it's going to run. Right? So that would be a while loop. What other loops do you know? In C, you have a do while loop. Right? And what is that? What's the difference between while and do while? You would read code like this um, in C quite often. Right? this is your while loop, and you also have this version. Something like that. Here we do some programming. The difference is the while loop may execute 0 times. Right? So it's possible that the loop body will never be executed. Because if S is the empty string, then P, star P will be 0 already, and the whole loop body, which is usually something like, if we do a conversion, to uppercase, or just for whatever reason, I just want to add 32 to it. Right? This may execute 0 times uh, if this, because this is a C++, a C string. So it would be H, E, L, L, O, and then there's a 0 there. So if my string is empty, then it will immediately fail. Do while loop is guaranteed to execute at least 1 time. So that's the difference between those two. Now in Python we have this one, we have counted loops, we have while loops. Actually, technically speaking, we don't have counted loops, we don't have 2 while loops, but we do have while loops. What other loops structures do we have? You know? Enumerate, yes, that's correct. So enumerate what? You were so close. I was already very impressed. This is usually called a loop. What we have to do quite often is iterate over elements of a container, where a container could be an array, a list, or some other data structure. Right? So this is often referred to as a for each loop. So we iterate over elements of a container. And in C++, for example, standard vector. Now this is a more modern loop, but it turned out to be really useful. So most of the modern imperative programming languages have a for each loop. C doesn't have one. C++ didn't have one when it was first designed in about 1990. But nowadays, modern C has one, and you should definitely use it. Python has one, and in fact, Python doesn't even have the counted loops. In Python, everything is a for each loop. So when you write for I in range 10 or range length of the list, then that looks like a counted loop. But in fact, the range is a function and it generates a container for you. Now, it does it very efficiently. So you never actually have to deal with the container. It's sort of a special container that can be dealt with more efficiently. But that's how you can do counted loops. Now what it basically gives you, range gives you a list. The return of range is a list that goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not the terminating value. So you can have range 4 to 12 implement or free. 8. 12 add 4. Okay. Then this is the start, stop, and this is your increment or adjustment. This can also be negative if you want to. So this will start, this will return a list, sort of, that has 8. And then the 8 plus 4 will be 12. But 12 is not included in the list. Your terminating value is when the list terminates. But it's not included in your lists. So for I in range 10 will give you the numbers from 0 to 9. For I in range length of the list will give you the numbers from 0 to, if your list has 5 elements, it'll give you numbers 0, 1, 2, 3, 4. And then you can use those numbers for indices. Right? Because indexing in computers is 0 based, not 1 based. So that would allow you to iterate over an array, which is what I do here. In this solution, your solution to the homework, right? And I think you have the same. Okay, yours is slightly different, but it has the same effect. I'll just leave this now. Those two pieces of code are basically equivalent. They're doing pretty much the same thing. My version, I start at 0 and compare to 1. And if 0, list of 0 is less than list of 1, then I append a 0. probably wrong. There's a couple of ways to do that. So I leave it here like this. If the element and then the next element is less than, then I append a 1 into my list. If it's not, then I append a 0. Then ignore that part. Then at the end, I check if the sum, which means if I add them all up together, if that's equal to the length of the list minus 1, then every test succeeded, and I can return true, and if not, then I return false. That's what your solution did. This is just another way of going through the list. Here we start at 1, and we go to the length of the list, which is not included, so this will be our last element. And then I can compare to my predecessor. So here I start at 1, so I compare 0 to 1. Next time through the loop, I compare 1 to 2, 2 to 3, 4 to 5. This one does the same thing, it just is a different how we talk about the neighbor. Like you're looking to the neighbor on your left, and I'm looking to the neighbor on the right. But both of those are the same. And then this is the code. However, it's not really such an elegant solution because you wouldn't want to write it like that if you were to run that in a real program. And the reason for that is actually, make sure this actually works. So 0, 1, 2, 3, 4, 5, 6 is true, right? But this is not how you would want to write this code, because if I have a list that is 1, 0, and then a million numbers, then in your solution here, you will look at all 1 million numbers, because you test each and every one of them. But that's not necessary, because I already know it must be false when I check the first two. So you want to not waste CPU cycles checking another 999,998 numbers that you know will never change the result. So here, This is how I would write it. So we're going through the list. If my predecessor is not less than me, uh, if my predecessor is not less than me, then it's strictly monotonic, it's impossible, so I set my result to false, and I then can use break, just like in C and C++, to break out of the loop. Then it just means stop the loop right there. I already know the value. So this will only do 2 comparisons as opposed to a million comparisons. In your version, if we pass in 1, 0, so this will be much more efficient code to deal with the problem of strictly monotonic. And this will be a good solution for this particular homework. Now, if you were to write this in C++, then it would look also very similar. Because in modern C++, the old way would be to use a counted loop. So you would write for int I is equal to 0, I is less than numbers dot, is it length or size? I think size in C++. Numbers I, this would add them up. This would be old style. And you shouldn't use it for new code anymore. This would be wrong, in my opinion, if you code this in C++. The new style would be using a ranged loop, which is how C++ calls their for each loops, and then something like that. So the advantage there is when you're iterating over containers, this one here is more error prone. Right? Sometimes you forget to write the I++. All of a sudden, your for loop would sit, your program would sit in an infinite loop. Because if you don't change I, then it's always going to be the same I, it's just going to execute forever. Also, you may check the size wrong, or the size at wrong times, and things like that. So, even C++ has sort of embraced that particular loop. Now, as far as Python is concerned, one of the other crucial things, which is probably the most divisive feature of of Python is that of semantic indentation, or semantic white space. And the difference is that in Python, you need to indent your code properly. Right? So Python does not use curly brackets like in C or C++ or Java in order to encapsulate blocks of code. In Python, it's all done by how far you shift things to the left. So here, the for loop starts here and ends there at the break. Right? Those three lines are part of the for loop. And we know that because the for loop requires us to start a new block. So there's a colon at the end of the line saying that there's a new block. And that must be there for a for loop. And then the next line must be shifted over, must be indented to the right. If I don't indent it, then the Python interpreter is going to generate an error saying that the indentation is wrong. It says expected an indented block, but didn't get one. So something is wrong. You can indent your code by anything from 2. I can also make it twice as big, the indentation here. That doesn't really matter. Okay, this matters. And some people are very much against this. I actually think it's a very good idea. Because when you read this code, it actually doesn't read so much different from C or C++, right? Except from the C code that you're familiar with. However, this program and this program So for a C compiler, this program here will actually work just the same. Right? It's exactly the same as the previous code that we have. Because in C, C++, Java, the blocks are all indicated by curly brackets, which means the compiler can parse this. Because, but you've never seen C or C++ program like this, right? It always looks like that, or similar to this. And the reason, of course, is that programmers need to keep in their head what's actually going on. If you write everything on one line, that's totally impossible to do. And even if you are a genius that could do it, nobody else could. So if you ask a friend to look at your program, they wouldn't understand the thing. Right? So the problem with C and C++ is that everybody uses indentation anyway in order to structure their code, in order to make the structure of their code visible, but the compiler uses a different representation. The compiler uses the curly brackets in order to divide up the code into blocks. But that can cause a problem if the two are out of sync. Then you end up with bugs that are very, very difficult to debug. Very difficult to find these errors because when you look at it, you see one representation, but your compiler sees a completely different program. So if when you're trying to figure out what's going on, you end up with a program that is quite difficult to find an error in. And this can happen quite easily. So for example, in this program here, C++, if numbers something like this, right? And your input, make it C, and here's some C program. What's the output of it? what will be the output of this program? S equal to 3? No. So you're trying to debug this. Now your output is actually going to be 0. It's going to print out that S is equal to, actually, yeah, it's going to print out that S is going to be 0. But why? This is really hard to find, and it'll take you a while. At the end, you'll figure out that this semicolon is what messes everything up. Right? If you look at the indentation and everything on the code, then it's pretty clear what I was trying to do. Right? I wanted to count how many threes there are, which is not a very difficult problem. It should be very easy. Right? But this semicolon messes everything up because pardon? Correct. The syntax for C is that you have 4, and then the thing after the 4, the next command is going to be repeated, wrapped by this loop. Right? But what's the next command? The next command is the next thing that follows in your program. The next thing that follows here is a semicolon. A semicolon is a no-op command. It is a command that does nothing. So basically, you run the loop, but you don't actually do anything in this case. Your loop is terminated. Then you have the curly brackets here and here. Now, curly brackets indicate another type of command, a command block. Several commands grouped together that should be executed as part of your loop. And that's what initially was clearly intended by me. Right? I wanted to execute this part here. From here to there, I want this to execute for every time, every number here. But what really happens is that I say for every number do nothing, okay? And then check. Now at the end, I'm going to be pointing at whatever value is here. I'm going to check if that's 3, then I add 1, and then I print it out. So the problem is that your mental model, the indentation, is different from what the compiler sees. It's very difficult to find those errors. So Python does the right thing, in my view. Python actually says, well, if the programmers are using indentation in order to, if programmers are using indentation in order to structure their code, then the compiler, the interpreter, should also use the indentation. So these kind of errors are totally impossible to have in Python. There's no way that you have an error where your interpreter sees a completely different program from what is shown on the screen. And there's another way you can do the same thing with if then else. You can have a then and else. Any kind of semicolon is a valid command in C and C++ and Java, but it's not what you usually intended to do. So I think this is a very good thing, but you must be aware of it. So you must indent your code correctly. But even if you've written C and C++, you did the same thing just for your own sanity, right? Because it would be impossible to think about the program if the whole thing is written as one line. So the Python, Guido von Rossum, the inventor of Python, one of the original Unix hackers and Plan 9 hackers, he designed Python in 1987. That, I think, was a smart move to make. The reason why this changed was because in 1987, we had more programming power available. So now our compiler still runs fast enough, even if it has to do. The job is harder for the compiler now. Right? It's easier to just parse something that's denoted by curly brackets. But I don't think our job should be to make it easier for the computer. You want to make programming easier for the human programmer, not the compiler. So we have loops, iteration. Another component that we need for imperative programming is also shown in the program here. We need to worry about conditionals, because otherwise our computer can only execute statements in the exact same order. So even though you can write something, iterate over that loop, you can always ever execute the same stream. But you want to be able to do things like if it's an odd number, you do this. If it's an even number, you do something else. Right? So we need to be able to change our control flow. That's called conditionals. And in Python, they're pretty much the same as C and C++. You have if then else loops. That's a standard setup for imperative programming language. C, C++, all of them have if then else loops. Assembly language, I'm not sure what you would call the assembly language. Assembly language would be branch on equal, branch on not equal. So assembly language really only has if and else. But yeah, it's the same thing really. That's one way of doing conditionals. Any other ways that you are familiar with? So there's no surprises really in Python when dealing with conditionals. So if x is less than 5, print I, else, print that would be a standard if then else conditional in Python. Now, in C, you also have C and Java, you have one more conditional, which is the switch, which we don't have in Python. There's no switch statement. And there's something, so if you wanted to do that, you basically, let's say, C is equal to input enter key, and then you can go if C is equal to S, command is equal to start. Else, now if I wanted to have, want to program a game, so S is to start, and then W is to go forward, and A is to go left, and that kind of thing, then it actually gets a little bit annoying. Because if I have a big chain of those conditions that I have to test, then because of the fact that white space is meaningful, that it has semantic meaning, I have to keep pushing things to the right. So you can see if I have like 20 different commands, to check here, every time I have an else, I need to go to the right. So after 20, the whole code will be over here. So that will not be very easy to follow. Not very easy, will not look very nice. Will be hard to keep track of what you're checking when. So Python, this will work, but Python, because of that, has a special keyword. Else if. And then last we can so this is syntactic. This really translates into else, if, and then indent everything to the right. Here now you can have a chain of things, and you don't need to push towards you don't need to indent your code towards the right as you program. So this is the equivalent of a switch statement in Python. So if you have an else followed by another if in a block with a block within it, then you would replace it with an else if, elif, in order to just maintain your same indentation. And that's how you would do the switch statement in C and C++ would be exactly for this kind of scenario where you need to check many different possible cases. So this is conditional. individuals. Now, what else do we need to know for our imperative programming language? These three are really the key aspect of imperative programming languages. Most of the programming language books have those as important concepts for programming languages. I include another couple which are sometimes covered at the beginning, sometimes at the end. Another thing you need to know is how to define variables. So even if you don't want to learn Python, even if you want to learn Python++, or no, not Python++, some totally new programming language. No, Go is already exists. Taiwan language. Taiwan government decides to implement their own programming language. You've never heard of anything about them, but you are a foreigner, you move to Taiwan, you have to program in that, right? If your coworker tells you it's an imperative programming language, then if you know these three things, you can already start writing code pretty efficiently. But you also need to know how to declare variables and how to use variables. So when it comes to variables, programming languages can be broken down into two camps. One are the static types, statically typed languages. The other ones are dynamically typed languages. Or some mixture of those two, which is what modern C++ now is doing, in a sense. So static type programming languages are C, C++, and Java, and Fortran. Actually, Fortran only has integers. No type there really. In C, as you can see, if I define a variable, I need to specify its data type. Int, double, string, standard vector. I need to say what that variable is. And then I can do things like int x is 3, x is equal to 4. You need to know how to do assignment, but assignment is usually with some more form of equal sum. So sometimes people, some programming languages, Pascal, it has to be colon equal to do assignment. Python, C, they just use equal sign. So that's easy. You can change the values. However, what you cannot do is change the type. So you cannot, this would be illegal in C and C++. Because I defined x to be a variable of type integer, but now I want to use it as a floating point or as a string. All of these would be illegal. In Python, that's not a problem. I don't need to define. Python is dynamically typed, which means we don't define the data type for a variable. The data type of the variable is only checked when you execute the code, not during compilation or interpreting the program. So x is equal to 3 allows me to define an integer variable, 3, for which I call x, and it has the value 3. And then I can, of course, reassign it to 5 if I wanted to. Or I can also reassign it to a string, and the compiler will just execute that. So when I execute the line print x, then the program starts executing. It will check the data type of variable x, which in this case is a string, and it will print out a string value high. Then I can set it to an integer again, and I can print that as well, and it's going to print it out. So Python is a dynamically typed programming language. You can reassign variables, different types. You can also mix things up. So for example, if I have a list, since the types don't matter, I can define a list y like that, and I can mix things, right? Integers, floating points, strings, and put them all in one list. So that means in Python, we don't actually have the need for structures. Like C and C++, you usually have struct something in order to group together two integers, a floating point, and a tuple of something. You need to define that as a type. But in Python, since the interpreter doesn't care, only when you execute it, you don't need to define structures. You can just build the structures. You don't need to tell the compiler saying, hey, I'm going to start building these things now that contain two integers and a floating point number. Now, the types are tested at runtime. And the values are, the operators are overloaded. So plus, for example, when I have two integers, then x is 3 and y is 5, and then x plus y is going to call integer addition like you would expect. I can also do that for strings, except when I call it with two string arguments, then it's going to do string concatenation. It will put one string after another. Right? So this is also quite intuitive, quite natural. This is what you would expect to happen, I think. However, if you now change y, then what will happen? This will now give you a type error, because now when the Python interpreter executes x plus y, it's going to check the type of x, which is a string, I, and the type of y, which is an integer, 5. And in this case, the Python interpreter says, because when you have dynamic programs and you can switch around variables, it is sort of very easy to say, oh, then I just switch it to, if I want a string, I just go to the weaker type. Like I automatically convert every integer to a string if I need a string. But that actually leads to a lot of problems in programming languages. So Python does not do any implicit casting, it's called. It doesn't convert the type of your arguments to a weaker type. Often that is not. If you need that to happen, then you need to tell the compiler. You need to do the automatic conversion. And of course, you have casting functions to do that. But here, in this case, it's going to say x is a string, y is an integer, and you want me to combine those two with a plus operator. I don't know what you want me to do. And then it will fail, give you a type error message. So if you want to execute this, then you need to convert the type of y from an integer to a string, and then you get i5. Which actually turned out pretty funny. Yes. So now you get a i5. So SPR is the casting function that takes an argument and converts it to its string representation. Or int to convert something to an integer. Or float in order to convert something to a floating point variable. So those are the main sort of points of concern when dealing with Python and variables. And we also have what I call modularization, which is how do we take a large programming problem and break it down into smaller manageable parts. And of course, the standard way to do that is by using functions, subroutines, and modules. So what's the difference between a function and a subroutine? Subroutine. Used to be in programming language design, people would make a big distinction about that. Functions are subroutines that return a value. And subroutines are blocks of code that you can execute with by calling them. So subroutines will be functions that do not return a value. But nowadays, that distinction is pretty minor. It's not a big deal anymore because in Python, everything is a function, because if you don't return anything, the interpreter is going to return none automatically. So if we have this code here, and to generate a function, you use def to define a function, and then one other thing that I really like about Python, the new Python, is the format strings. Those are pretty nice, and you don't really have them in C or C++, but you can sort of have templated strings. You can say that you want to generate a string, and by putting an F in front, and then putting your expression in curly brackets, then I can get the output here. So x is 4, y is 5. We'll just print it out nicely. And as you can see, I don't have a return statement here. But if I don't return anything, the operating system is going to, Python runtime is going to return none, which is the null value for Python, which is called none instead of null. But of course, if I want to, I can also return something from the list, from the subroutine. So let's return a list, just because we can, and then the return will be the list 456. So the point I'm trying to make with this class, by the way, is not just to learn Python, but also how to go about learning any other imperative programming language. Right? Those are the things you need to worry about first. Once you know those, then there's usually a couple of special features that programming languages have that you still need to learn in addition to that. But you can already start writing basic programs and read basic programs, and then grow your understanding of the language. There's a couple of modern programming languages that are popular now that you may have heard. You already mentioned Go. So Go, a lot of this is very similar, in fact. Go is also developed by Google, so the ideas are the same. But Go would add, in addition to the imperative programming paradigm, Go is an interesting language because it adds what makes Go special, and I think very good for systems programming at the moment, is that it's the only language that focuses on parallelism. So in Go, you can very easily generate threads, processes, in order to um, run things in parallel. And if you want to write an efficient program on a modern CPU, then invariably, very often you have to figure out how to parallelize your program, because your i7 already has 4 cores on the die itself, right? 4 or 8. So you already have all of these processors, but if you write your C program, it usually will just run on 1 core. So 7 of those are not used. Right? They're just sitting idly by doing other jobs for the operating system, but that doesn't help your particular application. It doesn't help your program. Go uses basically the same idea as Octave. You have channels, you can send messages from one process to the other process. And that means that to write highly efficient code, you need to be able to do that. So if you have a language that makes that easy, then you're much more likely to use it and be able to write efficient parallel programs. So Go would be one. How about, you may have heard of Rust. How about Rust? What's special about Rust? Rust has this notion of ownership. It's trying to solve a particular type of problem that we have in programming languages. If you want to write, the old style of programming in C and also C++ was to use malloc and free and allocators, constructors and destructors in order to allocate memory. Right? The modern way, Java then was the first, not the first, was the first mainstream popular programming language to use a garbage collector. So in Java, you don't actually call malloc and free. You simply allocate, you call a constructor, and then you use your program, and after a while, the program will stop, and it'll go through the memory. If you allocate something big again and it doesn't have enough room, it'll go through the memory and then check for things that are not used anymore. Then it will call the destructor, then it will delete them for you, right? So that's the more modern approach. There are advantages and disadvantages to both of those. It's also a different kind of way of thinking about that. C and C++, basically, it's a little bit more like every time you live in your room, and every time you drop something, you clean it up right away. And the garbage collector approach is sort of, you just live there, and once a week, you start cleaning up all your, or you wash your clothes. Once a week, you just wash all the clothes in one go. Whereas in C, the idea is that every time you have a dirty piece of clothes, you wash it. Right? Bam, bam, bam. So every time you have to clean up that area, you have to do less work, but you have to do it more often. So now, it turns out that writing this malloc and free code is very error prone. Lots and lots of bugs. Tons of security problems came in because memory was free, but then your program still accessed it. So it's a very big security issue. To write secure programs is much harder if you have to maintain the memory. It's much easier if your operating system keeps track of the memory and then deals with it for you. Now, the downside of the garbage collector is that you have to do a lot of work. Possibly, if you need a big block of memory, then you also all of a sudden need to do a lot of work in order to clean the whole room or clean all your clothes. But the time at which that happens is outside of the control of the program. So sometimes if you write a game, you would have a game and it runs for several minutes and you can shoot all the bad guys, and all of a sudden the garbage collector kicks in, and then this all has to be cleaned up. So then it would, for half a second, nothing would happen because your operating system would clean up. Your garbage collector would clean up. So those are the two approaches for memory management, and Python uses garbage collection. So you don't actually delete anything in Python. In general, for sort of simple programs, this is a good choice, because garbage collectors, of course, there's been lots and lots of research into how to implement an efficient garbage collector, and they've been getting better and better over the years. So now we can sort of amortize minimize the cost of the garbage collections, we can come up with ways in which we can use the memory and delete it better. However, the other problem is with when it comes to memory management, where do you actually allocate the memory for a variable? So where is it actually generated? There's two parts of the memory that you can use. One would be the main memory in your program space. So that's called the heap, and you have a huge, most of the heap usually starts at low memory, and you can keep allocating more and more memory. Another block of memory is called your stack space, which is usually where your processor stores the return address so that you can call functions and go back to where you called from. So this stack space has an advantage when it comes to dealing with memory because when you leave the function, then all the variables are automatically deleted because that memory is going to be reused for other stuff. So you don't need to call the destructor for everything, right? You can do that much faster. So you want to keep things on the stack if you can, but the problem is if you want to return something, then it cannot be from your own subroutine. So this works well in like subroutine 1, subroutine 2, subroutine 3, all with different namespaces. In this case here, in our program here, in your solution, if we look at this code, then result in this code, if we look at I, right, then I is in scope only for that for loop. After the for loop, actually it's still in scope. It's only in scope for this particular subroutine. So when I return from strict monotonic, I will disappear. No other program, no other part of the program can access I because it simply is gone. And there's no pointers to anything in Python. So that means I can just allocate it on the stack, I can do the computation, and then I return and boom, all of this is gone. So that's really nice. However, result is actually the same thing, right? Because it's defined there. But now I need to be more careful because now I return the result. So what I actually need to return is that value. I cannot destroy a result now. Otherwise it'd be gone. And then I would not be able to print anything out. So the value of result now needs to be moved from the scope of strict monotonic into the program that actually called it. And that means you don't want that result here now strictly in the stack. You want to return this, you want to move it to the outside scope. And so Rust, these kind of errors, it's pretty tricky to keep track of all of these ownerships and where pieces of memory are. On the stack space or in the heap. And Rust, sort of has this idea of ownership made explicit. So it makes it easier to write correct programs that have to do fairly complex memory management using Rust. Because they basically attach with every piece of memory, not only do you have the value, but also you have this notion of ownership. And whoever is the owner of that memory has to make sure that that memory is deleted not too early and not too late. But that makes it easier to write secure programs, correct programs, safe programs. So that's what makes Rust an interesting programming language at the moment. And the whole thing, though, is with calling constructors and destructors, there are issues. So, for example, at the beginning, when Java, first versions of Java, you had problems because in a more complex scenario, instead of just freeing the memory, you also have to call you want to call the destructor when the memory disappears, right? Now, for a list or a vector or anything like that, that would work fine, right? You have a block of memory in the heap. If you need more memory, then you call the destructor and say, okay, I want to get rid of you. You clean up. Then it cleans up itself, and then you can reuse that memory. However, if you have a file, an external resource, then that's not so clear anymore, right? Because you write or a printer. If you want to print, you need to open the printer, right? Then you can start sending data to the printer. Then when you're finished with your job, you need to close your printer, right? So that the other program can use it. Otherwise, nobody else will be able to print. But when you write a class printer in order to deal with a print job, then, of course, it makes sense. You would say, oh, in the constructor, I open the printer. In the destructor, I close the printer. Because I'm done with it, right? But then the issue was that when the destructor was called, actually depended on, in the initial version of Java, would depend on the only chance you had was by the garbage collector. So if your program didn't use any memory, then you may be in a situation where your program printed out one page 1 hour ago, but it still controlled the printer because you hadn't actually called the destructor yet. So those were all things that you need to worry about. Or database connection to the database server or files. But there's only a limited number of those, right? So if you run too many programs, if you run just one program, you wouldn't notice it. But if you run too many programs, all of a sudden you will be out of external resources simply because your program didn't keep track of them the whole time. It kept them open, and the garbage collector hasn't called the destructor yet. So then you realize that you need not just the destructor, but you need a proper ready to destruct. I'm finished now, and whatever the garbage collector wants to do now can happen afterwards, for example, and you want that code executed. And then you have a whole bunch of issues if you do that style of programming, if you have exceptions, because then you may jump over entire destructors may or may not be executed at the time that you expect them to execute. So garbage collection is an interesting topic as well. Memory management in general is a difficult and error-prone problem. Most of the modern programming languages are popular. One reason I think is just because for the garbage collectors are now so good that most applications you can just use them and not worry about them, and your program is going to run just fine. talk about lists some more, or let's try and do. Another exercise. So try and implement a function, replace vowels, which has as input a string S and a character C, and then if you have a vowel which is A, E, I, O, U, then you want to replace it by C, whatever that character is. So if you have a string, hello world, for simplicity, all lowercase, and I call it with Z, then it should return H, Z, L, L, Z, W, Z, R, L, D. So try and implement that in Python, and even if you don't have a Python interpreter, try and write it in Word or Notepad or something for now. So just replace, take a string as input and then replace every A, E, I, O, U, one of the vowels, with whatever I pass in as the character C as another argument. Okay, so I just checked the CPUs just out of interest, but it's not as high as I thought. So the Intel i7 sixth generation is 2 billion transistors, and the AMD Threadripper 3960 is 3.8 billion, so about 4 billion. And VPU number, but my usual the Wikipedia then cannot load at the moment because the internet is too slow, so I can't get the exact numbers. VPU RTX 3080. Yeah, so the GPU numbers have been going up, so it's about 28.3 billion now. So a GPU has many more transistors, 4 times, in this case 10 times as much as your CPU. So actually I would have thought that and the power consumption, 350 watts. Wow. And I don't know, there's a RTX 3090 and a RTX 3080 Ti. They seem to be the same as far as. And the A100 NVIDIA compute chips for deep learning, 54 billion transistors. So here, let's see our little programming exercise. Replace the vowels. Yeah, okay. This line is not exactly Python. You cannot just write it like that, but pretty close. And you, yeah. Except I would call that list vowels instead of list. I would give it a different name, but never mind. So one nice thing that we have in you may be writing something like this. Now, I basically want to say if SCI is equal to A, or SCI is equal to E, or SCI is equal to I, right? So on and so forth. That would work. That would be one way of writing it. Python has, however, a nice function called in, which checks if something is in a collection. So this is much more concise. So I can just say if SCI is in the vowels, then I want to replace it with the character. Now, if S, whether this works or not, is actually now undefined. The way that I intended it to, it will not work. However, under some circumstances, it will work. So what's the problem with this code? What I wanted to do was replace hello world. Oh, and one thing that's different between Python and C++, you'll see we don't actually have any character data type. In Python, the character is only a character if it's a string that has a length 1. That's the only constraint. So there's no difference, so there's no type char in Python. If I run this, I will get an error because yeah. Okay, so the problem is that for the string, strings are immutable in Python. So I cannot assign a value, I cannot change a string. So here when I execute SCI is equal to C, it's going to give me an error saying you cannot do that, you cannot do item assignment for strings. The only thing we can do for strings is convert them, append them basically, right? And there's a whole bunch of other functions for strings, like extracting a substring, finding a substring in a string, and things like that. The kind of functions that you would find in the string library in C and C++, but I cannot change the string. So why is that? In fact, most modern programming languages now default or prefer to use immutable strings because in general it's much more efficient to be able to do that. So one of the reasons is that in fact I can take the string, right, and I can actually put it, if I'm doing an embedded programming project, I can actually put it in ROM. It doesn't need to sit in RAM. Right? Because if I can ever change the string, then I can just use that string and put it in read-only memory instead of standard memory. Because I won't be able to override it anyway. The other thing is that I don't really need the string then, the values, right? Unless I want to print it out. So I can actually exchange the entire string for a single reference, a short pointer basically. And everywhere where I use the string, I just compare the, or I just use that pointer instead. It also removes aliasing problems. That is to do with, again, memory management and parallel processing. Your Intel CPU, often, if you deal with strings, you have to copy a string from here to there, right? During the processing, if you need to do that, copying a block of memory, because it happens so often, your CPUs have special instructions to do that very fast, very efficiently. So to copy a block of memory from one part to the other part, there's a special instruction that can do that very quickly, but it only works if the two blocks of memory are independent. So if this is your source and then you copy this block of memory into here, then that will work nicely. Right? That's not a problem. But often, especially when you do garbage collecting and you move stuff around in memory, sometimes what can happen is that the source and the destination overlap. So then it becomes more difficult. So here's your source, and now you want to copy this into this block of memory. Right? So you want to take it from here and shift it to there. But now the tricky part is that if I start doing that with my very fast instruction for copying, I will actually get the wrong result, because this piece will be copied here, this will copy there, copied here. So I overwrite the memory. So then the next row I'll copy, that one is okay. So I fill up all of this memory, but now when I write this part, I will read these values that I already overwrote, right? So for this to work, the order in which I do things is very important. So here, in this scenario, if this is my source and this is the destination, I need to go from the end. I need to say, copy this one in here, copy this one in there, copy this one in there, copy this one in there, right? And then I can go towards the start of this block. Then it's okay. Then this copying will happen correctly. So, okay, why don't we just program it in such a way that we always go from the end towards the beginning? Well, if your destination is here and your source is here, now that will do the wrong thing, right? Because you're going to copy and overwrite values here. So depending on if you want to move blocks of memory and they overlap, you need to be very careful about where the source is and where the destination is. And you need to do all of these checks before you can use the fast block move operation. That one really only works if the two blocks of memory are not overlapping. So that means that your operating system that doesn't know where you want to copy things always has to use the slow version. By making strings impossible, it's guaranteed that we don't have any pointers inside of the string. So I'm guaranteed that source destination is always going to be different. They're never going to overlap. Since they're never going to be overlapping, I can always run the fast block move assembly language instruction. So my program is much more efficient when dealing with strings, assuming that I don't generate too many of them. Java is the same. Strings in Java are also immutable. So if I want to do that in Python, then I could do things, I can deal with that. One way of doing it would be to say that S is the list that I generate. So I explicitly passed it from a string to a list, and then here I return I cannot really return, I would have to return the join of that list. That would work. Converting it to a list and then taking the list, converting it to a string. That's not how I would write this though, because I would have to remember about strings and lists and all of that. It's easier to just use a second string, because one thing that is very efficient is appending to strings. Right? So I simply, when I need to have a string that changes, I simply go through and build another string, keep appending. If you add things to the end of the string, it's quite efficient. If you put things at the beginning, it's slightly less efficient, but also still manageable. It won't be such a huge slowdown of your program. Both of those versions will work, except if I also want to sort of reuse codes as much as possible, so I would probably replace this to show that the control flow branches and then unites again. I would introduce an extra variable there, saying that the only thing that changes is what I append, but I always append. But that is really just style choice. Both versions will be fine. I like this one just a little bit better. Okay, so that's for strings. The other thing that you also want to familiarize yourself with is that you can, in lists and strings, you can do indexing and slicing very efficiently. And that's actually pretty nice. So I can use list. List is zero indexed, so list 0 would be the first element, 1. And list 1 would be the second element, which is a 2. Some nice things about Python, I can also generate indices or sublists easily. So I can say I want the list from index 2 up to but not including index 6. And that will return me a sublist 3, 4, 5, and 5.6. So that's all the elements from index 2, 3, 4, 5, but not index 6. Right? So now I can generate a sublist. We use that very often in Python. And of course, I can also have a list 0, 1, 2, 3, 4, 5, 6, which is in itself a list. So lists can be nested. I can have a list within a list. And one thing, this in C or C++, that would be an error, right? Access of -1. In C, that would give you, that would allocate, it would access the element that is to the left of the beginning, which doesn't, it's undefined. But in Python, this is actually well defined. So -1 means count from the end of the list. So if you want to get the last element of the list, that's always list -1. So you can get fast access to the first element, list 0, and the last element, -1. You can also use that to slice things. So I can go the last 3 elements of the list. Sorry, the last -3, -2, but not including -1. So this would be the last, the third last and the second last element of the list, which is 5 and 5.6. So I think that's pretty neat over and quite useful in lots of situations, because often you need to manipulate the list or a string. Same thing works for strings. You need to manipulate the list from the end rather than at the beginning, depending on what kind of processing you need to do. That's also possible. Okay, good. Then that's it for today. Hopefully next week we will have our internet again, and we can do some introduction. We can actually start talking about kinematics for humanoid robots. So as homework, as homework, you may have heard of the Wordle game. That's very popular now, where you have to guess games. You have to guess words, right? So it would be like this, and now it belongs to New York Times. Have you played this game before? Okay, so so you need to guess a 5-letter word, okay? And which word do you guess in English? What word do you want to start with? So let's say winter. Oh, winter, I counted the number of words. wins, right? And then if you hit enter, it'll now tell you by gray, it'll says W is not in the word, I is not in the word, S, D, N are not in the word. So now you need to guess another word, but you don't want to use the W because it's not in here. So what other word can we guess? R, rocky. How about rocky? That would work, right? And you can enter, and now it says no C, no K, no Y, but R and O are in the word, but not in the right position. So the word has an R in it, but the R must be here, here, or here. And it must have an O in it, but the O must be in one of these three spots, or here. So what word can we think of? How about throw? Throw would work, maybe? No? Let's see. T, H, R, O, but W I already used, so W is a bad choice, right? It can't possibly be throw. So can we throwing, throw, drop, hard drop, not in the word list. And then draw, or, but what? Group, group may work, yes. Let's try group. G, R, O, U, E. Actually, that's a good guess. Oh, R and O are not there, or it could be swapped. So, or, or, draw, H, Laura Nixon, Morris, okay. So not sure. Don't really think of the word. Should be What? A board? I hope that's it. Oh, oh. Oh yes, so it couldn't be a board because it's always in the same position here, so we wasted a run. Huh? Spell again, wow. Oh, other. Yeah, maybe. Other. Ah, yes, you're the genius word player. Okay, very good. So, you want to write a function, guess and correct. There are two strings, right? 5-letter strings, and you need to return the number of characters that are in, so you need to draw this, you need to draw this, these ones are gray, these ones are yellow, and these ones are green. And here you have a set of indices, so you can draw them in the interface. So for example, other was correct, right? And my guess was rocky. So in this case, I want to return gray would be index 0 and 1. No, sorry, 1, 2, 0, 1, 2, 3, 4. So second, third, and fourth character are all gray. They are not correct, they're not in the list. Yellow is 0 and 1, and green is the empty list. And for other, I would return empty list, 0, 1, 2, 3, 4. Right? Because other, everything would be correct. And in this case, you would have solved your puzzle. Okay? So write the Wordle score function for this particular in Python. Implement the Wordle score function in Python. As your homework until next class. Yeah. Holiday. Oh, okay. Then 2 weeks from now. Is it true that next week is holiday? Okay. So whenever the next class is, the homework is to do the Wordle scoring function. Okay, then Did you join the server already? The NTNU server? Okay, good. Then we're going to check. Then you need to send a message like bang register. That's you.